In this lecture, I'm going to talk about Diels-Alder's reactions, which deals with dienes, and an intro to aromatic compounds, which will take us into electrophilic aromatic substitution in the next presentation. So Diels-Alder reaction is a cycloaddition reaction where we have a diene that's in its conjugated form, and it bonds with what is known as a dienophile, or something that loves dienes. And in our case here, we have 1,3-butadiene. Okay, and this process is going to be the same over and over and over again. I don't care what's going to be attached here, 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 here. Doesn't matter. Just focus on the conjugated diene and your dienophile. And we're going to end up with is known as the Diels-Alder adduct, which is going to essentially take these, bring them together, and make a 6-member ring. Diels-Alder reactions are known as 4 plus 2. 4 from my diene, 2 from my dienophile to make a 6-member ring. So let's take a look. All right, we can also use an alkyne as a dienophile, and we would still get a 6-member ring. Notice, we're not really worried about this and this. We're really focusing on here and here. And we're going to watch those double bonds move. So, what happens? Okay, my dienophile attacks my diene. Double bond shifts. Double bond leaves to make the other bond. So, one of the pi electrons from the dienophile makes our top of our ring structure. That causes one of our double bonds to move. And the pi electrons in our diene come out and bond to our dienophile to make the 6-member ring. So if I were really like numbering this or something and wanted to show you here, and we said, okay, this is carbon number 1, this is carbon number 2, let's say this is 3, this is 4, 5, and 6. Okay. Over here, this would be 6. This would be 1, 2, 3, 4, and 5. Okay. Just so you can follow along. Again, my conformation has to be in cis for this to work. Even though trans is our lowest, I need my diene to be in the cis form in order to close that ring. So I need it to actually be in the high energy to close the ring. Okay. And that's what this is illustrating right here. So let's take a look. All right. Different products we can get at different temperatures, and it all depends on your diene and your dienophile. And I know, if as you go along, let's start up here. Okay, this is what I would do every time. Number my carbons, and I don't care how you number them as long as you know where the 6 are. Okay, so what's going to happen? This attacks here, this bumps down here, this comes out here. Every time. 6, 1, 2, 3, 4, that was a terrible 3, right? 3. Okay. All right. Getting a little bit more complicated here. What's going on? I don't know. All right. Well, no, you do know. Okay. Here's my diene, a file. Here's my diene. What's going to happen? Number the carbons. Here's number 1. Here's number 2. Here's number 3, 4, 5, and 6. Okay. One's going to come in. This is going to move. This is going to come out. And over here, number them. 6, 1. What's attached to 1 now? Oh, I got to add that there. That's how I would do it. I would draw the ring out knowing that you're going to get a 6-member ring every time. All right. Let me go to the previous there. I didn't need to get rid of that. 4, 5, and 6. Okay. Now we do the same thing down here. This looks really complicated. Is it though? Because right here is my diene. Here's my dienophile. Number the carbons so you can follow it along. 3. Okay. Oops. 3. Sorry. 4. 5. 6. Okay. Over here. 1. Sorry. 6. 1. 2. 3. 4. 5. Like we did. This comes in here. This goes down there. This comes out here. Now, what is on the 4th carbon? Oh, there's a line. All right, let me draw that line in. Oh, there's one on the 5th. Let me do that. On the 1st carbon, there's this carbonyl carbon functional group. All right, throw that on. Okay, but it's the same process over and over. Now you see this term up here, electron withdrawing substituents and electron releasing substituents. So let's talk about that term. Electron withdrawing groups, those that want to be directly attached to the double bond. Okay? So a dienophile will have an electron withdrawing group attached to the double bond. Something that's going to pull electrons away via the inductive effect. That's a good dienophile. The better the dienophile, the better the diene, the better the reaction. So if we go back a slide really quick, not so great of a dienophile, an alright dienophile, and now a more substituted diene. More substituted diene, good. Better electron withdrawing group, better dienophile. Hence, this one needs 200 degrees in pressure. This one gets a little bit better. I don't need pressure, but I can lower the temperature, but still a high temperature. This one, great dienophile, great diene. Boom, 30 degrees around room temperature. And we're moving along. A little bit hotter than room temperature. Okay. So my dienophile, I'm looking for an electron withdrawing group. Carbonyl carbon, a nitrile group, something like that. Good electron withdrawing groups that I want to see on my dienophile. Aldehyde and ketone groups, carbonyl carbon stuff. Something that's going to have a good inductive effect, something at the double bonded O or the triple bonded N, something is going to pull those electrons along. Good electron with releasing groups. If my ester is bonded to the carbon with the oxygen and not the carbon. Okay. An ether and any alkyl group. So I want these on my diene. I want these on my dienophile. Now we're going to look at a bunch of examples of our reactions. Here, they're not drawn in the cis form. And they're drawn the line structure way and not the skeletal way. But that shouldn't concern you. Find your diene. Here's my diene. And here's my dienophile. I'm going to put a heart. Okay. Here's the double bond. So here is carbon. If we want to do it the same way we were doing it, 1, 2. All right, we'll call this one 6, 5, 4, and 3, like so. So what's going to happen? This is going to come to here. All right. This is going to shift into here. And this is going to come way down here. So if I were numbering these, what carbon is this? Well, this would be carbon 2. Because that's the one I numbered to be attached to that. Where is this one? This one's going to be around carbon 5 and 4. So if that's the case, okay, and we move along. So here's 2, 1, 2. All right, this would be 3, this would be 4, this would be 5, and this would be 6. And however you want to number them, whatever you want to do, as long as you could see what your product is going to be. Okay. And they're showing it, they're breaking it down this way. If you want to do it that way and need to break it down that way, that's fine too. I like looking at the numbers personally. Same thing here. I know you're looking at it and saying, oh my God, what's all this over here? And oh, this looks so intimidating. And oh, I don't know what to do. Well, let's take a look. Here's your Diena file right there. Here's your 1 and 2. Here's your 3 or 6 or whatever you want to call them. But here's your 6 through 3 over here, however you want to number them. This is going to attach here. This is going to attack there. We're going to have a methyl group hanging off. So let's say we called this 1, this 2, this 6, 5, 4, 3 again. Okay, and we did everything the right way again. Dupe, move it, and come all the way over. Okay, so this would be 3, this would be 1, this would be 2. This has to be 5 there, so this will be 4 with the double bond. 5 has the methyl group in the double bond, and 6 is sitting right there. Drop better 5 out. Okay. All right. You could try breaking this one down yourself for a little bit of practice. Now there's a triple bond there, but nothing changes. This is still your Diena file, except we're just going to keep one of the double bonds. So this one here is equivalent to this here. And there's still this one here to attack and do your entire reaction. And again, they break it down for you on this. Oh, they don't break this one down. I thought they did. We could do it. But I'll leave it there for you to do it. But again, it's going to be the same thing. This is going to go here, here, and here. Just try numbering your carbons out and see what you think. Okay. Now, a conjugated system, one of our most famous conjugated systems is benzene. Okay, and what benzene is, all right. I have a tough time drawing it with chalk, let alone, let me just undo that. That looks terrible. All right, let's try this again. So go here, 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 and there. Okay. Well, let me do it. I could probably draw a better freehand than I can there. So here's benzene. Benzene's known as an aromatic compound, has alternating double bonds, hence the term aromatic. And it's a conjugated system with alternating double bonds. The electrons are constantly moving. It's a 6-member ring. Okay. The electrons are constantly moving. So, let's see where we were. We were here, now here, and there. And we just keep them going. So some people draw benzene this way. Since the electrons are constantly moving and never staying in the one place, they'll draw it like that. Okay, so this is benzene. Conjugated system, alternating double bonds. Aromatic, alternating double bonds. If we want to draw it out, the full skeletal, or I should say line way, it's going to look like that, with a double bond here, a double bond here, and a double bond here, and each one is bonded to a hydrogen. Okay. No one really draws it out that way. When we start getting into ring structures, everybody goes with the skeletal way, assuming that you know that there's hydrogens there on our ring structure. All right. So what happens is I could start substituting functional groups onto these benzene rings or ring, and they have specific names. Now you should get comfortable with the names. You should get comfortable with these, the combined names and the singular names. Okay? Chlorobenzene, bromobenzene, ethylbenzene, nitrobenzene. Straightforward. The functional group that's on there, all right, plus the word benzene. But some of them, so this is called ethylbenzene, but this one down here is known as methylbenzene, but we don't call it methylbenzene, we call it toluene. Toluene is the name that is most commonly used, just like styrene there. Benzoic acid, it's a carboxylic acid on benzene, benzaldehyde. So you would say, well, this one is what? I have a ketone, so why isn't this called, benzenone or something like that? I don't know. So it's called acetophenone. All right, benzonitrile, it's not called benzol, it's called phenol. Anisole is there, that looks like an ether, right? Aniline, which we'll get back to when we get to our nitriles and our nitrogen compounds and our amines, and benzosulfonic acid. So you should be familiar with these names because they're going to come up and you may see them on an exam in the future on a Thursday in July of 2020. You should be familiar with how to name or seeing these compounds. Okay. Now, how do I know whether I'm known as, if my benzene ring is a side chain, it could either be written as a benzyl or a phenyl group. Okay? It's a phenyl group if it's directly bonded to the chain. As you can see here, I do have a double bonded chain right here. Okay, right here. And the group is directly bonded to it, therefore it's a phenyl group or phenyl group, depending on who you talk to. If there is something in between, it's known as a benzyl group. If there's a CH2 in between, this could be a longer chain, it could be a bromine like it is, an OH, whatever it is over here. If there's a CH2, then the benzene group, then it's known as benzyl something. Phenyl if it's directly attached, benzyl if there's the CH2 connector. Now comes the fun. Okay, and the slide's a little small on this, so I'm going to show you on the board. Okay. There's a few ways to name di-substituted benzene rings. Now, the first thing I'm going to point out, whatever group the functional group is on, okay? So we'll put a functional group there. It doesn't matter. This is the number 1 carbon. And as you can see, my benzene rings suck. And I know they suck, and I've been told that so many times by students and peers and everything, and I try and I try. But that is always the first carbon. Okay? There's another way. Okay, that one's not so bad. There's another way to name these or number these, but it's really not numbering. It's position from the functional group that's added. Okay. If I'm... Oh, I forgot to draw these in here. Okay, and you have to make that sound or it doesn't work. If I'm one away in either one of these positions, this is known as the ortho position or O position. If I am here or here, all right, there's a gap in between. I'm 2 away. All right, the red is known as the meta position or M. And last but not least, whoops, let me get a different color. What I use, green, black. This spot right here is known as the para position or P. Okay, so I want to name a compound. Okay, we'll start here. We'll put a chlorine on, and this is known as chlorobenzene. Okay, pretty straightforward. Now let's say I put another chlorine on. I don't care where. Let's put it here. Okay. How would I name this new compound? Let me use a different color so I can leave chlorobenzene up there so you see it. Then show it to you this way. Okay. How would I name this? Well, if I go IUPAC 1, 2. Wow, look how I spelled chloral there. Yikes. Chloro. Okay. Chlorobenzene. Because I'm on, look at this, I'm on fire right now. Benzene. Okay? Because I'm on the 1, and then I go shortest distance to the next thing, 2. I could also call this, all right, if I wanted to, and since it's 1, 2, don't forget we need a di in there. But I can also call this ortho dichloral benzene. I can also call this O dichloral benzene, and all of these are correct. I know what you're going to say. So, which one do I need to know for the exam? All, because all are accepted. Okay. All are accepted. I could do it the 1, 2 way, I could do it the ortho way, whatever it is. Okay. What if they're not both chloral? What if one's a bromine? Okay, and one's a chloral. And I'll zoom it in a little bit. Well, we go alphabetical order like IUPAC says. 1 bromo, 3 chlorobenzene. We could call it metochlorobromobenzene. We can call it M-chlorobromobenzene. If you wanted to call it M-bromo, all right, that doesn't work. I mean, it does. I'm not going to take points off. It's not the end of the world. Like down here. Well, how do I know? What is this? Okay, well, it's 4-hydroxytoluene. Well, how do I know it's not 4-methylphenol? Listen, you put it as 4-methylphenol or paramethylphenol, and you don't remember that it's cresol or cresol, I'm okay with that. Okay, but the names, again, you should know the ortho position, the para position, and the meta position, also knowing the 1, 2, and 3 names. Okay, so there's many different ways to name di-substituted benzene rings. Now we're going to talk about the reactions that get those on the ring. This is kind of leading us into that. These are known as electrophilic aromatic substitution, which will be in our next chapter. How we become reactive, how we become polar, all depends on the functional group. So benzene has a certain reactivity. Adding a functional group to it could either make it increasing that reactivity or decreasing that reactivity. Okay, and there's orthoparameta, like I said. And again, the functional group will depend or determine whether I will be orthopara or meta. So that ends this one. It's a short and sweet one. This one gets combined with, again, it's a precursor to EAS reactions, and it's kind of like topping off talking about addition reactions. So it's a nice in-between, and there's that. Okay, if you have any questions on this, please feel free to email me.